Hi everyone, we're going to continue on with chapter 11. So today what we're going to be talking about initially is going to be how we can convert alcohols to make them good leaving groups. So we talked about using strong acids in the last lecture, so we can use something like hydrobromic acid, hydrochloric acid, or hydroiodic acid. Another thing that we can do is we can actually react alcohols with sulfonyl chlorides. So what sulfonyl chloride is, it's going to be something that looks like this. So we can have any R group, so anything containing hydrocarbon, carbon, and hydrogen. So these are going to produce sulfonates. So remember, a sulfonate is a good leaving group. So this is something that we looked at in chapter 6 and 7. So again, sulfonates are good leaving groups. So if we can convert the alcohol to a sulfonate, we can then further react it with another nucleophile to get the desired product. So what can happen is that in the presence of a base, so the base, something like pyridine, is needed. So we take our alcohol here, we have an alcohol and a primary carbon, we react it with our sulfonyl chloride, which is shown here. Again, our solvent in this case is going to be pyridine, and then what happens is we are going to produce this tosylate, it's called. So we would have our OTS, this is an abbreviation, remember, for sulfonate. So since we know it's a sulfonate, again, this would be a good leaving group. If we look at the actual mechanism for this type of reaction, so first we have our starting material. We would have, I'm just going to show the sulfonyl chloride as an R group so I don't have to draw out the phenyl ring. So what happens, don't forget we have lone pair electrons on that oxygen. It's going to form a bond with this sulfur. These electrons are going to go to this oxygen. So remember, sulfur is one of those that likes to have an expanded octet. That's why all of this is possible. So what's going to happen here is the chlorine is going to leave. These electrons are going to go here to form a double bond. What we'll be left with is going to be something that looks like this. So we have our pyridine, which again is going to be a base. So it can actually deprotonate this hydrogen here. So when that happens, these electrons are going to go here, and what we will be left with would be our tosylate. So again, sulfonate's good leaving group. So if we were to react this with something like sodium iodide, for example, so we have Na+, I-, our nucleophile here is going to be our I-. What would happen is we would have an SN2 reaction, and this would be our product that is formed. So remember, we would have inversion of stereochemistry if this was a stereo center. So this is one way to convert, again, alcohol to something to make it a good leaving group. We also have, like I mentioned, the acids that we can use. Another thing that we can do is we can actually convert to a bromide. So conversion to bromide, I should say, is by using phosphorus tribromide. So we can treat with phosphorus tribromide. We can use both primary and secondary alcohols, and these will be converted to the corresponding alkyl bromides. So if we have, again, we'll kind of look at the same starting material that we just looked at. So we're adding, again, phosphorus tribromide. What will happen is we will replace the OH or the alcohol with a bromide. So if we look at the actual mechanism for this, what happens, these electrons are going to go here and form a bond. One of the bromines is going to leave. What we have next is going to be something that looks like this. Oxygen has that plus formal charge, which we wouldn't want. So this is going to make it a good leaving group. As that's leaving, the bromine that left, so this one up here, is going to come in and attack. So we would be forming this product here. So this is an SN2 reaction. So since the reaction is SN2, it will occur with inversion of that configuration at any chiral center or stereocenter. So let's look at an example with stereochemistry. So if we have something like this plus our phosphorus tribromide, so again, what's going to happen is we have inversion of our stereocenter. So this carbon right here. So this will be important if you're trying to like devise a synthesis or something like that, and you see that there's inversion at that stereocenter, then you would know that you would want to use something like phosphorus tribromide, for example. Another thing that we can do is we can convert to chlorides. So using something called sulfonyl or thionyl chloride. So when we treat with thionyl chloride, we can use again primary and secondary alcohols, and these would be converted to the corresponding alkyl chlorides. So let's look at this example right here. If we use thionyl chloride, so this is thionyl chloride, and then typically something like pyridine is used. So again, some base. So remember, pyridine looks like this. What we're going to have again is going to be inversion, and we are putting the chlorine in place of that alcohol. We would also have SO2 gas plus Cl minus. So let's look at the actual mechanism for this. So if we look, we're going to have something that looks like this. So again, lone pair electrons on the oxygen coming in here to the sulfur and attacking. These electrons are going to go to the oxygen. What we're going to have is going to be something that looks like this. One of the chlorines is going to leave. These electrons are going to go back to form a double bond. So our next step is going to show our formation of that double bond. Again, we have our solvent, in this case, pyridine. So again, base is going to abstract this proton here. These electrons are going to go to the oxygen. What we'll be left with is this right here. So this is going to leave. This chlorine is going to leave. And the chlorine, or the halogen, well, chlorine iodide, chlorine ion that's formed is going to come in here and do a backside attack. So we have, again, our SO2 gas, which is coming from here. And then we have a chlorine ion, which is coming from right here. So let's look at all the different methods that we really just talked about. So if we have something like this, and we were told to devise a synthesis to synthesize this compound here. So a couple of things you want to note. You want to note that overall we have inversion at that chiral center. So that's going to be important when we're thinking of how we can get to this product right here. So if we were to use, so what we talked about initially, so remember we talked about the sulfonates. So we can react with the sulfonyl chloride. So this right here is an abbreviation for what we used earlier, that toluene sulfonyl chloride. Again, it can be any R group coming off of here. But again, when it's toluene, that benzene ring with an extra methyl, that's going to be called toluene sulfonyl chloride. So with that, we have retention of the stereo center. So if we were to react this with sodium iodide, right, this would be an SN2 reaction, and we would be able to have our inversion at this stereo center right here. So that would be one way to synthesize it. If we were to try this method, so if we had this starting material and say we wanted to now get to this product right here. So we would have to take a different approach because we're retaining that stereo center, right? That configuration at that stereo center. So what would happen here? First, we could have something like that phosphorus tribromide. So that would give us inversion, right, at the stereocenter. So if we have inversion, then what we can do is we can have another basically inversion at that stereocenter. So something like sodium iodide would be SN2. So we would invert this stereocenter again to give us this product. So the overall retention is shown as a configuration, but really this is achieved by a double inversion. So what we're gonna do is we're actually gonna skip Fischer esterification. So this is all of page 7 in your notes, and then the top of page 8. So if you're taking Organic 2, this is something that they're going to cover in Organic 2. So the last thing that we're gonna talk about is gonna be the Williamson ether synthesis. So with the Williamson ether synthesis, what we do in this case is we are going to look at alcohols that are going to be deprotonated to form alkoxide. So an alkoxide is this. And then these alkoxides, they can react as a strong nucleophile with either like an alkyl halide or an alkyl tosylate. So this is going to be an SN2 process. So what typically happens are ethers are produced. So sodium hydride, is shown like this, or sodium metal. So sodium metal, remember it has the little 0 indicates that it's going to be sodium metal, or metal I should say. So this is generally used as the base. So it's going to completely deprotonate the alcohol. So let's look at an example of this type of reaction. So if we have something like this, we have a 2-step process. So we have either sodium hydride or sodium metal, either or can be used. And then we can use a tosylate. So remember this is sulfonate, so it's going to be a good leaving group, which is important. So what we can do is we can have, these electrons are gonna go here. We're gonna have so we have sodium hydride, so Na plus, H minus, this is gonna come up and steal that proton right here. We're gonna have our alkoxide plus hydrogen gas. And then what we have is our second step. So what's gonna happen here is this is gonna be like an SN2 process. So this group is going to leave. And then our product would look like, so we have 1, 2, 1, 2, then we have an oxygen. And then we have 3, 4, 5. So we have 3, 4, 5. So this would be our product right here. Another example of a Williamson ether synthesis would be something like this. So we have, this time we're going to look at 2 equivalents of this alcohol. So we'll use sodium metal this time. Again, it can be either sodium metal or sodium hydride. And then we will have this alkyl halide. So what's going to happen here, we're going to have sodium metal, right? That's our first step. So we're going to produce that alkoxide. So with the production of that alkoxide, we also have hydrogen gas. And then we are going to have basically an SN2 reaction, or 2 SN2 reactions, because we have 2 equivalents of this alcohol. So what that would produce would be, so we have, right, this is going to be our alkyl halide. So we have the production, so let's number these ones, 1, 2, 3. So that's kind of our starting point. And then coming off of each of these, we have this tert-butyl. So again, with the Williamson ether synthesis, what really happens is you are going to deprotonate this using either sodium, this proton right here, using either sodium metal or sodium hydride. You're going to produce an alkoxide, so OR minus. Once you have the production of that alkoxide, what's going to happen is you're going to have an SN2 reaction with either an alkyl halide or an alkyl tosylate. So think about stereochemistry when you're doing these reactions, right? So since this process right here is SN2, we would have inversion at that stereocenter, if it is a stereocenter. So a lot of times these are going to be ethers. So an ether is an OR group. So, right, we might not have a stereocenter in this specific case. So, but it's something to think about overall when you're doing SN1 reactions or SN2 reactions, what the configuration at that stereocenter should be. So again, practice all the reactions from chapter 10 and 11. There will be a combined quiz on that material. What we need you to do is really think about how you can devise a synthesis. So you'll be doing that a lot in Orgo 2. There will be a question like that on the quiz also. So you're going to have to, starting with really, let's say something like this right here. I could ask you, so this is probably more straightforward than what would be asked on a quiz. But if I asked you to devise this synthesis here, you would have to think about, again, configuration at that stereocenter. You have to think about how it's retained or how it's inverted using either the phosphorus tribromide, or using the sulfonyl chlorides, or using thionyl chloride. So it's a lot to think about, but again, if you really understand the mechanism behind all of these reactions, it should help you when you are doing these practice problems. So if you have any questions, please reach out to me, and I hope everyone has a great day.